This video is going to be about means. So the data set that I'm looking at here is the Little Basswood Lake Catch data. I think this comes all the way back from problem set number 1 and identifying quirks in the data. This time we're going to use it to talk about means. So I'm focusing on the species and the fin length that were given in the data. I quickly created a pivot table that took the species and counted the number of rows for each species, as well as took the average or the average fin length for each species. Again, because it can be difficult, Excel can be kind of finicky about doing math directly in pivot tables, I've just copied this and put it over here so I can reference these cells directly. Now, prior to Math 105, if you were asked to calculate the average fin length from this particular data, so don't worry that it's an average of an average at the moment. If someone were to ask you to calculate an average, you probably would do something like 209 point, etc., plus 277, plus 0, plus 452, and work your way down, and then divide by the 9 data points that are here. So let's do that. Let's calculate the average, and that is the sum of these numbers. And we're going to divide by the 9 numbers that are there. And so we would tell whoever asked us that the average is about 173. Since starting Math 105, I'll note that we tend not to use the word average a lot. Instead, I have been referring to the mean. And that's because there are 3 different kinds of averages. We have 3, if you call the average the same thing as the central tendency, we have the mode as an average, we have the median as an average, and we have the mean as an average. So in order to avoid confusion, we've been using the term the mean in this class. And to keep things confusing, there were 3 different types of means that we talked about: an arithmetic, a geometric, and a harmonic mean. Now in the class we have exclusively been referring to the arithmetic mean, and we will continue to do that here. That's the only one we're going to talk about. However, under the category of arithmetic means, we learned about 2 different options there. There was the equally weighted mean and the unequally weighted mean. Now note that those are the options, and it's not an unequally weighted mean and an unweighted mean. Now, all arithmetic means are weighted means. They all have weights. So the question isn't, does it have a weight or not? The question is, are the weights equal for each data point, or can the weights differ between data points? So if we go back to the kind of average, the pre-Math 105 average that we did, it was, again, the sum of the values divided by the total number of values, and we get a number. That average, we now know, is the mean, and this corresponds to an equally weighted mean. And we'll go prove that kind of at the end of the video. Before that, let's go contrast this with an unequally weighted mean. So the unequally weighted mean has a formula, and it is something kind of like this. We're going to take the sum of a value that we care about, and we are going to give it either more or less importance than it would normally have by multiplying it times W. W is the weight, so a large weight makes it more important, and a small weight makes it less important. So we'll take our value and we'll sum it or multiply it times a weight, and do that for all of our data, sum that up, and then we will divide by another sum that is just for the weights. That kind of puts everything in the right scale, if you will. So that is our weighted average kind of formula. This is a bit longhand, but perhaps the best way to demonstrate it. Let's go work this out, and work this out kind of piece by piece. Let's go create a new column here that is x times w. So x times w is the data that we care about that is adjusted for its relative importance. So in this data set, we have an average, and we have a number of fish. So the average fin length is, or the fin length, if you want to think about it that way, is the number we actually care about. And then we're going to adjust these according to how many data contributed to that average. So the number of fish is going to be our weight. This is just a slight variation to some of the data sets we've seen, where this is a survey result or something like that, and this is the number of respondents or a total population. You can think of number of fish as number of people. It's the population. And if we have a number of things in our data set, generally that is what we want to use as our weights. So here we're going to have fin length as our x, and number of fish will be our weights. Our equation says we need to take x, fin length, times w, number of fish. So let's do that. It is the fin length here, and we're going to multiply that times our number of fish, and that is our first x times w. That is for that one data point. We need to do this for all of our data points separately. So that's 277 times 2 is 554. It shows there. 0 times 2 is 0. We go all the way down. So those are all of our x times w's. We then need to take the sum of those. So let's take this average and scoot it out of the way for the moment. So we will say this is the sum. Just so we don't get confused. Here we are, the sum of x times w. So there's a number. So we can ask ourselves, well, what is the interpretation of x times w? And what is the interpretation of the sum of x times w? And honestly, there is no real physical interpretation. When we're done with this, we will have an average, a weighted average, but the x times w component and the sum of x times w doesn't really have any convenient way to think about it. Some of it's like a variance. Remember a variance? At least in one of the examples we used, it was squared salmon. Well, squared salmon doesn't make any sense until we take the square root of that. This is kind of the same thing. We have a value which is this times this, but in and of itself it doesn't mean anything. So now we have the sum of x times w, that component. We still need the sum of w, so let's do another sum that is over here. And this is equal to the sum of w. So number of fish was our weights. So we will take the sum of the weights, which is 632. So that is the denominator, so we need to take this top part divided by the bottom part, and we'll get a weighted average. And that is equal to the numerator, the sum of our weights times x's, divided by the sum of the weights by themselves. And we get a similar but different value. So if we take the fin length and we take into account the number of fish that contributed to this, we get a slightly smaller value than we would otherwise, than if we treated each of these as contributing equally. Generally, especially if the numbers are somewhat close, you're probably better off taking the weighted average. Ultimately, this is a question that is specific to your discipline, whatever it is you're looking at. But by default, if you have the option of doing a weighted average and your weights are on something that makes sense, weighted average is probably the way you want to go. So we've calculated the normal average, kind of the pre-Math 105. We calculated a weighted average where the weights are unequal. Now I said before that all averages are really weighted averages. And that would imply that this one that we did ahead of time should also be a weighted average. And indeed, we can use the exact same equation. This is the generic weighted average formula. So we can use this same equation to get this number. Here we had our weights that were unequal. Our weights were equal to the number of fish. So in order to get this, we need to have an take an equally weighted average. Instead of the number of fish, these numbers would all have to be the same thing. So let's try that. Let's do x times w, and we'll specify this is, that's not x times x, x times w, and this is specifically for equal weights. Before that though, let's come up with a weights column specifically. So let's just arbitrarily assign a weight for each of these species equal to 1. So instead of saying that the BBC fish will be the most important because it contributed the most, because it had the highest weights of anyone, we're going to say that BBC has the same weight as CWS, is the same as NOP, and the rest. So we've specified our weights. We do the same thing, x times w, so equals, x is still our fin length, and weights, in this case, we want our new equal weights. And we want to do this for every data point, so we'll just drag that down. So this is saying average fin length times 1 is 209, 277 times 1 is 277, and we keep on going down. The next step in our equation, just like before, is to take the sum of all of this. So let's do sum I can type. And scoot that over so it's clear. So this is equal to the sum of x times w. And then we want the sum of the weights. Well, that's inconvenient, so let's do the sum over here. The sum of the weights. In this case, because the weights are equal to 1, this is the same thing as the sum of the data points. We'll bold all of these so we don't get confused and think that they're real data. So we have 9 data points. We give each a weight of 1, so it's a total of 9. We then want an equal weighted average. That's what we're calculating now. And so following this formula, we have this numerator, we have the denominators. We want the top part divided by the bottom part. There is our top part, the sum of x times w. There is our bottom part, the sum of weights. And we get our equally weighted average is the same as the pre-Math 105 normal average that people expect. So thereby demonstrating that this is the average, or this is the way to calculate an average. And the question is just whether or not your weights are equal, or if your weights are unequal. As one last demonstration, one could argue, and looking at the equation, we took the sum of values and we divided by a total number of values. And if we look at what we did here, we have the sum of values. Everything was multiplied by 1, so it's just the original values, divided by the total number of values. So of course it's the same thing because we literally had the same numbers, and that is perhaps an unconvincing argument. So let's do a second weighted, or equally weighted average, but instead of our weights being 1, let's make our weights some random number like 23. Now, since we're calculating an equally weighted average, it doesn't really matter what these weights are as long as the weights are the same. So we have to make the weights the same for everything. We now have a new sum of weights, so that's our denominator. We have a new x times w, so it's still fin length 209 times 203 in this case. We have some new values. We have to take the sum of that, there's the numerator. We still take the unfortunately, that's in the way. We take the sum there, and we divide by the new sum of weights. So let's do that. It's equal to the sum of our x times w divided by the sum of our new weights, and lo and behold, it is still the same thing. As it should be. Here is again just our generic, this is the way to calculate an average. It is a weighted mean. And it's just a question if our weights are equal. Doesn't matter what the weights are, as long as they're equal. We still get the same answer. Or if our weights are not going to be equal and we are taking into account, for instance, the larger contribution of this particular fish. And we can see since our weighted average is smaller than our normal average, having more of these I would say more of these smaller fish. No, these are actually larger fish. So there are kind of interesting patterns going on. The BBC contribution, the x times w is rather large. So this is driving the overall average up, but then we have some values that are driving the average down more. And overall, it seems like these smaller fish are driving down the average compared to an equally weighted mean. Anyway, hopefully that explained some things about weighted means. This is kind of the painfully tedious way of doing it. Just for completeness, perhaps I'll quickly demonstrate some Excel functions that allow us to do some shortcuts. In particular, the shortcut is that x times w. Instead of having to create a new column for this, you can use a function called the sum product. And there's the function. You can see it wants some arrays. An array is effectively a variable name. So we want, for instance, the average fin length as one variable, and then we hit the comma, and that bumps it up to array number 2, another variable. This is the weights column for us. That is where we stop. So we close our parentheses there. That gives us the sum x times w. So we still have to take this and divide by the sum of the weights, which for us were number of fish. And we can see there's our 164.5, which matches our 164.5. So that sum product command is just a shortcut for this column. Okay, I think that does it.